is going to talk about spontaneous creation dynamics and interaction of vortices and Bose Einstein condensates.
Thank you very much for the introduction, and I would like to thank the organizer of the conference, and in particular Klaus, for giving me the opportunity to present the results from the BEC Center in Trento. This is a joint effort of experimentalists like myself and the theoreticians. In particular, on the experimental side, we have in the group two permanent, Giacomo Lamporesi and myself. Tom Bien-Aimé just left the group as a postdoc. And currently, the PhD student most involved in the experiment is Carmelo Mordini. On the theoretical side, the group is led by Franco Dal Fovo with Lev Pitayevsky. And we have very strong interactions with the theoreticians from the Newcastle University, in particular with Nick Proukakis, who's present in the audience, concerning the finite temperature and quenched measurement. And Carlo Barenghi with Luca Galantucci about the study of condensate, the dynamics of condensate at zero temperature, the zero temperature. And also have to acknowledge the funding from the National Institute of Nuclear Physics and the local province of Trento. So the outline of the talk is actually like the title. So it's about, we discuss about how we create vortices, how we study the dynamics and their interaction. And in particular, I will also spend a few words about the characterization that we did and their properties in the setting that we have in the experiment. So let me remind what we are working with. We are working with Bose Einstein condensates, which are the states of matters where we have a macroscopic occupation of the ground state. So this means that the state is a coherent state, and it can be described in terms of a single wave function, which is in the limit of macroscopic occupation, essentially a C number, where the amplitude is the square root of the density, and then we have a phase factor here. And this makes such that the system is a superfluid, which means to flow without viscosity, bringing, for instance, to the paradigmatic fountain effect in helium-4. And also, it supports quantized vortices. We know that superfluids are important also in nuclear reactions and are high relevance also for the study of neutron stars. So how do we produce BECs? Actually, we start from our favorite gas of a bosonic particle. In our case, is sodium atoms in the thermal regime. Where the atoms can be, where the particles can be described in terms of billiard balls, simply because their de Broglie wavelength is much shorter than the interparticle average distance. Then by cooling, we increase the de Broglie wavelength until the limit where the de Broglie wavelength becomes of the order of the interparticle distance. And then the Bose statistics enters into play, and we start occupying macroscopically the condensate. This means that at this point we have a spontaneous symmetry breaking because we have to choose the phase factor here. Okay, so how do we do this in the experiment? Typically, we start from a vapor. We just heat up the sample and cool it first by laser cooling, which means we use radiation pressure in order to reduce the temperature to the cold regime. We call this cold regime because still the phase space density is much less than 1, which is the condition for which the atoms have start to condense. And so in order to bridge the last 7 orders of magnitude of increasing the phase space density, we transfer the distribution into a conservative trap where we continue the evaporation, the cooling via evaporation. So we transfer typically the sample in an electromagnetic trap, whereby applying a radio frequency field, we are able to control the depth of the potential in order to force the evaporation down to the degeneracy. And typically we get about 10 million atoms into the condensate, almost pure. Almost pure means that we are able to remove essentially all the thermal components so that we get a pure condensate which looks about this way. Typically the size is of course much smaller, but the system is essentially elongated because the radial frequencies are about a factor of 10 larger than the axial frequency of the harmonic oscillator, and we have a very good symmetrical symmetry. The asymmetries in the trap are less than 10 to the minus 4. So, how do we detect our vortices? Typically, we are not able to detect anything in situ because the spatial density are too large. So, in order to see to get our signal, we let the system expand ballistically by switching off the trapping potential, and we do the so-called resonant absorption imaging, which means that we shine a laser beam, which is resonant on the atomic transition. Atoms scatter the light all around, and from the information contained in the shadow, we are able to reconstruct the spatial density of the distribution. Typical images are like this. As you see here on the left, we have one thing I have to say is that in situ our distribution is elongated like a cigar, and because the system is superfluid, we have a hydrodynamic expansion that transform the initial elongated distribution into a pancake, like this. And typically, in this case, we observe the cloud along one of the radial directions. So in fact, in situ, the system was elongated in the horizontal direction, and after ballistic expansion, we get this distribution. As you see here, we have a smooth distribution with sorry? Yes. So in situ, typically the size of the condensate depends on the number of atoms that you put in. In our case, it's the typical length is of the order of 200 microns. The ballistic expansion, of course, allows for the expansion of the condensate. So here, for instance, in these pictures, the side of the field of view, the vertical side of the field of view is about 2 millimeters long. This is very important because, for instance, as we will see later, the defects become sizable. So here the typical dimension of the structure of the features that we will discuss later is of the order of many tens of microns, which corresponds to the healing length at these densities, which are very low, simply because the sample did expand. In situ, the healing length of the condensate, so the size of the vortex, is of the order of a few hundreds of nanometers, which is too small to be observed by optical means. So expanding the condensate is essential in this case in order to avoid the problem of saturation in the absorption process, and also in order to increase the size of the defect that we want to study. Okay? Yes. Yes. So in principle, it could be the wave packet spreading just limited by diffraction. In fact, it is not like that because the mean field interaction, the content interaction of between the atoms increases the energy of the system well beyond the energy of the harmonic oscillator. So in fact, what you're observing here is an asymmetry which is imposed by the geometry. So because vertically, so which is the radial direction is more confined. So you may say, oh, this is simply the diffraction limit. This is the Heisenberg limit. In fact, it's not, because if you calculate what is the kinetic energy released during this expansion, it's larger simply because the chemical potential of the system is larger than the harmonic oscillator. Okay, and the typical procedure, so here we see on the left the smooth condensate. This is the ground state of the condensate, but in some cases we see some additional features that clearly do not belong to a ground state condensate. And actually the probability to observe and the number of the defects that we observe here does depend on the speed at which we quench the system across the phase transition. So here in this sketch I have in the horizontal, in the x-axis, the time of the quench across the phase transition that happens in this yellow region, and on the vertical scale, the frequency of the radio frequency that sets effectively the height of the potential in the magnetic trap. And for long quenches, we get this kind of sample in average, while for fast quenches, we get this, where you can clearly recognize some weird features. So what's the origin of this? All this belongs to the physics of the Kibble-Zurek mechanism, which I would like to recall. The point is that if we start from above, from a non-condensed sample, and we cool, since we have to break the symmetry, and if we cool slowly, the information about the symmetry breaking has the time to propagate within the system, and in the end we get a homogeneous sample, an homogeneous condensate. On the other hand, if we cool fast, regions which are apart within the sample do not communicate each other how the symmetry breaking happens in each point. So in the end, you have different orders parameter that develop defects at the boundaries. So this is the main mechanism. Of course, we need a second order phase transition in order to control in an effective way the speed of the cooling. But okay, so this is how it works. And actually, the Kibble-Zurek mechanism was observed already in various systems in condensed matter physics, starting from the 90s in liquid crystals, in helium-3, in annular Josephson junction, and also in ion crystal chain, where they were studying the configuration transition from a linear distribution to a zigzag when you increase the axial confinement. And more recently, there was it became very popular also within the community of cold gases. For instance, the very first demonstration was made by the group of Daniel Stamperkorn, from whom we will hear this afternoon. And later, it was observed both on the classical thermal to BC states, and also on quantum phase transition, for instance, from the mod state to the superfluid. Okay, so in our case, the sample in situ is elongated, so you may imagine that the defects appear as along the direction of weak confinement, so you may expect that the defects developed into solitons, which after ballistic expansion becomes more visible. The picture is partially true, as we will see. Also, and actually, you can already imagine that there is something weird happening here, because if we had just a soliton within the sample, we would expect to have how to say defects with essential a structure essentially planar, while in some cases, like here, you can recognize a kind of twist, which is centered around this point. Okay, so a couple of years ago, when we first observed this effect, we did a characterization of the probability to observe the defects in the average number of the defects as a function of the quench time, and we found the expected power law dependence. And we'll not enter into the details of these studies because from now on we will use this mechanism to produce vortices in a stochastic way, and also because tomorrow Nick Prukauskis will probably spend a few slides discussing on our joint work about the finite temperature physics of this system. So let's say, so what about the nature of the defects that we have? So at the very beginning we were observing the defects along one of the radial directions, and we recognized that from time to time the defect didn't have the expected planar symmetry. For instance, let's say that here and here and here we have a planar symmetry, but in some cases we have something which does not remind a plane. So in order to, and also there is there are some expectations that some calculation that tells us that in general in a 3D system solitons should be quite unstable on the typical time scales that we wait in order to observe, in order to produce the condensate without thermal fraction. So there was something wrong with that, so we deepened on that, and we added a further imaging direction in order to take simultaneously the picture of the sample along two orthogonal radial direction. And in that case, we realized that in some cases we did observe the planar defect both along both orthogonal direction, like here and here, but in other cases the twist was present either in the vertical direction as here or in this horizontal direction. But in none of the cases we could observe the twist along both orthogonal directions. So in order to understand what was going on, we added a third imaging direction along the symmetry of axial of a weak confinement of the harmonic oscillator of the harmonic trap, and then we realized that the structure that we were observing were always connected to the presence of the nodal line of what is a vortex, and depending on how the nodal line was oriented with respect to the radial imaging axis, we could observe the twist, like in this case or in this case. Unfortunately, the visibility here is not that good. But if the nodal line has an angle with respect to the radial imaging, there was no way to observe the stripe. So we were a bit surprised about this observation, because typically the presence of vortices is associated to somehow a stirring. For instance, you take your bucket of helium-4, you stir, and then you produce vortices which have an orbital angular momentum which is parallel to the stirring, of course. And in such a situation where we don't stir, we were still expecting that vortices should be aligned along the direction of cylindrical symmetry, but in fact it's not the case. It's not the case, and actually we should not expect that, because an elongated condensate can sustain vortices even along different direction as the direction of cylindrical symmetry, simply because the system in general, while it's cooled, tends to minimize its energy. So let's say that we impose the presence of the vortex because its topological excitation is intrinsically stable within the condensate, so we can admit the presence of a vortex. But in order to minimize its energy, we should rotate the vortex in order to put it in a radial plane. This is the configuration that minimizes the energy. And in fact, if you do the full study of that, you realize that the vortices typically of course, bring an orbital angular momentum. But on top of that, because of the constraint imposed by the geometry, have a excitation, have a phase pattern field that is essentially concentrated along the planes, radial planes. And so this brings to the definition of solitonic vortices, because they are vortices which at the same time are localized in space, so they have a solitonic character. Because of this solitonic character, actually, the phase field is somehow concentrated, and this phase field maps onto a velocity field during the expansion, which in the end results in the presence of the twist. So in principle, starting from the orientation of the twist, we are able to reconstruct what is the direction of the circulation in situ. Yes? The angular momentum is always 1 because the energy of a doubly charged vortex is higher than the energy of 2 singly charged vortices. So if you produce a doubly charged vortices, this would decay into vortices, into singly quantized vortices. Yeah. So the situation of what happens at the origin is very tricky. Actually, this was studied in detail by Nick. The point is that at the very beginning, we start from a turbulent system that very rapidly evolves towards a situation which is more smooth and which may contain vortices if the level of turbulence at the beginning was sufficiently high. It's a turbulent system, so it's quite complicated. Yeah. Yes. So actually, I was discussing about the determination of the vorticity from the twist. Actually, we could confirm this guess by doing a direct measurement of the circulation using homodyne methods, interferometric methods. I'm not able to enter into the detail now. There is not enough time. But the point is that by interfering a condensate with another condensate, let's say a copy of it, we are able to observe this kind of double dislocations that you can see here. Actually, there's a guide to the eye that confirm that depending on how the double dislocations are oriented, like this or like this, confirm that the orientation of the twist, whether it's an S-shaped or a Z-shape, does depend on the initial circulation. Okay, so this is just a general picture to show that we can produce vortices, but through a stochastic method. So we don't control the number of them, we don't control their position, for instance, along the axial direction, and we don't control even the orientation with respect to the vertical, with respect to the gravity. This is very nice. It's a very powerful, it would be in principle a very powerful setting where to study the dynamics of vortices and their interaction, but there is a big problem. Typically in atomic, with ultra-cold atoms, what we do is using this resonant absorption imaging, which is destructive. So in order to make a measurement, typically we fix the preparation parameters. We take a picture, then we change some parameters like lifetime, like the time within the trap, and we take another picture. So we start from a different realization. Of course, this method, destructive imaging, is not suited to study stochastically produced vortices. So in order to go on, we implemented a kind of a weakly destructive imaging method. So the key point here is that our condensate is macroscopically occupied. We have a lot of atoms within the condensate, and if we take a small fraction of them, and we just use this small fraction to study the properties of the condensate at that specific moment, in principle, we are not perturbing the system so much that the system will evolve as if we didn't take the picture. With the first method, we are applying microwave in order to do some small tricks that I will explain right now. So the point is that the atoms initially are in a given hyperfine state, which is the F1, MF minus 1. So here I represent the confinement within the magnetic trap. We apply a microwave field in order to transfer a few percent of the distribution to this F2. And this is crucial to the imaging because the imaging is always done starting from this manifold. And the imaging beam is dark to the atoms in this manifold. So we can shine the condensate with the imaging beam to observe the atoms in this state without affecting those that remain in the magnetically trapped. So in principle, we can take the picture, wait, take another picture. We can iterate many times until there are no more atoms left within the sample. These are the typical pictures that we get. Every column corresponds to one realization. These images are taken with some numerical filtering. Typically, we take the picture, the raw picture, we subtract a smooth profile, which is just the Thomas Fermi profile of a ground state condensate. We take the residual, and here we plot the residual. So here we have about 20 pictures taken at the different times. In this case, we have a vortex which coincides with this pattern here, which is still within the center of the condensate. Consider that here the x-axis, the weakly confined direction, is along the horizontal direction, and vertically we have one of the radial directions. We can somehow squeeze simply the pictures in order to simplify our interpretation. So the point is that here we are producing, for instance, two vortices that are moving along the axial direction. One is doing this trajectory here, while the other is doing a trajectory like here. And apparently, in this case, nothing interesting happens while they cross. But in general, we do observe interesting processes while vortices crosses. For instance, like in this case, where we have a change of visibility of at least one of the vortices. And also here, for instance, there are two vortices that somehow annihilate when they touch each other. There are, at that time, there were already some theoretical predictions about the dynamics of a single vortex within a harmonically trapped condensate that foresee the period for this precession of the order of the axial harmonic oscillator, with some corrections that take into account the intrinsic nature of the vortex and also the kind of the orbit that the vortex is doing, and the chemical potential. And actually, within a single realization, we could already check the agreement of our measurement with this prediction that was proposed both through some hydrodynamic theory and through solving the Gross-Pitayesti equation. For instance, here we can plot the axial position of the vortex for one realization, and from this axial from this orbit we can immediately determine just by derivation the period of the instantaneous period of the harmonic dynamics. Here you can observe, for instance, that there is a kind of chirp. the frequency of the oscillation increases, and this results simply from the fact that as long as we extract atoms picture after picture, we are reducing the chemical potential, and hence the period of the oscillation increases. Same thing happens for orbits, for larger orbits. And overall, we can say that we have a very good agreement between the measurements and the theoretical model. In these graphs, where I plot the period of the normalized period of the vortex, actually we have no free parameters. So the agreement is very good. But actually, there are some limitations. And this result from the fact that when we transfer the atoms to the bright state for the imaging, the atoms feel an anti-trapping potential that forces the that accelerates the expansion very fast. This is not ideal for from the technical point of view. And the other problem is that we have no information about the vortex orientation. Why I'm saying that? And the point is that if we had also the information about the vortex orientation, we could in principle do a full three-dimensional reconstruction of the vortex dynamics, which would be helpful in order to set some benchmark for the fundamental processes of vortex interactions, such as vortex annihilation, vortex decay, and vortex reconnection. So we just want to remind what reconnection is. The reconnections are those processes where we have two vortices approaching at short distances, at least in one point. And then we have a kind of topological reorganization of the vortices arms, such that we get from this configuration to this one. Okay? Reconnection are important processes in various fields of condensed matter physics, but not only, also in plasma physics and in high energy physics. And they were already observed in liquid crystals, which are unfortunately not superfluid. And they were also observed in helium-4. The problem with helium-4 is that, actually here the picture is not very good. There, in order to trace the position of a vortex line, they were adding some nanoparticles that somehow got trapped within the vortex core. The problem is that these nanoparticles, despite that they are nanoscopic, they are still many orders of magnitude larger than the core size. So actually, it is impossible to study at the microscopic level the reconnection with these systems. We would like to address this topic, and so we need to go a step further. And this is done by using the method 2 for the imaging. In this case, we do a two-photon transition, where instead of imposing a direct coupling from the F1-1 to the bright state, we go through the intermediate F1-0 using a radio frequency field. So here we apply a radio frequency field to couple the two Zeeman states, and then from this state here to here, we apply a microwave. What are the advantages of this approach? Actually, the point is that both this F1-0 and the F2-0 are insensitive to the magnetic field, at least to the first order. So we don't have the fast dynamic associated with the presence of the magnetic trap. And the second point, we are able to somehow apply a chirp on the coupling fields in order to refocus the atomic distribution while it is at the moment of the imaging. So, of course, refocusing the atomic distribution after the expansion is useful because this increases the visibility, the signal to noise. Of course, this is important, but there is another aspect which is even more important. So in order to introduce that, let's consider that our gas is trapped harmonically in the magnetic trap, but also in the presence of the Earth gravity field that imposes some sag. Okay, there is a sag which, in fact, means that the atoms are feeling a magnetic field gradient. And we exploit this magnetic field gradient in order to apply the outcoupling fields from the upper part of the distribution to the lower part. So we have a resonance surface that crosses the condensate, and we are able to control the position in time of these resonance surfaces in order to keep track of the free fall of the atoms that are already extracted. And the net result is that the distribution that we get into at the end is the column integration of the condensate, taking into account the phase profile within the condensate. So if we have a vortex, for instance, pointing within the board, on the left side we will get a constructive interference between the various contributions from the various heights. So we have a peak in the extracted number of atoms, while on the other side we have somehow a destructive interference, so we have a dip. And so from an asymmetry of the signal, we expect to be able to reconstruct the vortex alignment within the condensate. Actually, these simplified pictures can be confirmed by numerical simulation, and indeed we found that if the vortex is in the horizontal direction, we get this somehow dispersive signal with negative slope, while if the vortex is vertically aligned, we have a pattern which is symmetric. Of course, if instead of having a counterclockwise vortex, we have a clockwise vortex, the asymmetry would have an opposite side. Good. So experimentally, how does it look like? Here we have the raw picture taken at different moment. If you do the integration, remove the smooth path and part and so on, you will get here a signal which is a signal of the vortex which is like a sinus. Here in the intermediate picture it's symmetric, and here it's minus sinus. Of course, in between these pictures there are many others, and if you combine all of these after treatment, like this stage in a row, you will get a film of the position of the vortex plus an information mapped onto this let's say color map that tells us that there is a vortex which is orbiting at the same time is rotating. So here we have other cases of vortices that are precessing at the same time spinning. There are some extreme cases of vortices that are spinning very fast. And from this, we can somehow calibrate the information about this asymmetry in terms of the orientation of the vortex, because of the signal is periodic. So this is in principle very powerful. Actually, you may wonder, you may ask one question, and the question is the following. So at the very beginning, I told that the system is trapped in a highly symmetric cylindrical trap, and if we put a vortex in the radial plane, actually there is no reason to have a vortex spinning, because this would violate the conservation of angular momentum. So what's going on? The point is that if now you admit a rotation of the vortex line, of the nodal line, out of the radial plane with a given angle, actually the length of the nodal line will increase. So getting out of the radial plane has an energy cost, and so this means that there will be a momentum, a couple that tries to restore the condition of minimum energy. And actually this couple is responsible for the rotation, the overall rotation of the nodal line within the around the radial axis, the axial direction, sorry. Okay, so now we have some additional ingredients to study the interaction among vortices. What was done so far, Gelb, okay. So far, vortices were studied in a rather in a situation that was somehow not very interesting, because, for instance, if you stir the vortices, these become all align one another, so you can get these abrikosov lattice structures, where, of course, there is a strong correlation, but it's rather trivial. Or in effectively 2D system, the vortices behave like Coulomb charged particles, so you don't access the real 3D dynamics. In our case, we are interested to study the real 3D dynamics, because imagine this situation: what happens if we smash one vortex vertically aligned onto another vortex which is horizontally aligned? Something interesting might happen at short distances. In our case, the observable we have are essentially the position, of course, as discussed. We have the orientation in time, and also we have the visibility. Visibility may change, for instance, in this situation here, where the two vortices collide, and then we change, the visibility drops, and then may reappear later on. So just by comparing some numerical simulation with the experimental observation, we could distinguish various configurations where, for instance, the vortices were parallel oriented and orbiting one to the other. So this realizes the condition where the vortices in fact never cross. They approach but never cross. There are other situations where, starting by an orthogonal alignment, they may either bounce or reconnect or double reconnect. So these are numerical simulation, and actually we could distinguish the various events depending on the relative velocity, the relative alignment, and so on. And we found so far a reasonable agreement between theory and the observation. Still, the signal to noise that we have is not sufficient to let's say, distinguish between on the fine structure, on the details of the interactions, but still it's quite promising. And this is essentially all I have to say. Yeah, I'm out of time, so I just stop here. Thank you very much for the attention.